Okay.
I mean, he asked me to come today. I said, okay,
Okay.
why not? So
Cool, it can be nice. So, yeah, actually, just finish this. Okay.
Somebody looking for a mute button. Okay. Yeah, welcome everyone. I think we can start. Welcome everyone to this, and I'm going to say the whole sentence again, the Leiden-Delft-Erasmus Center for Sustainability Circular Industries Hub talk. So this is all series of talks for those that haven't joined before about circular economy, raw materials, criticality of raw materials, materials needed for the energy transition, etc. So we have a whole wide range of different topics that are being addressed in these talks. And today we have Malte Vogt, and he is an assistant professor in photovoltaics, technologies and applications at the TU Delft. And yeah, he received his PhD degree in optical characterization and simulation of PV modules at Leibniz University in Hanover in 2015, and he's now an assistant professor at TU Delft. He will be talking about, well, a very important topic, of course, because we all know that if we really want to move to a sustainable energy system and a renewable energy system, then PV is the main contributor to that. It should be at least, and especially in a couple of decades from now, should be our main energy source. And so we are building PV modules like crazy, I could say. I mean, you can see them popping up everywhere, and the whole situation with natural gas being blocked from Russia actually well, strengthens this push, at least in Western Europe, to move quickly to other energy sources. But we also note that there's a huge issue if it comes to the raw materials that are needed for this energy transition, and therefore, although at the moment, in the early growth phase, we are still and we need a lot of virgin input and a lot of virgin materials. In the end, of course, circular economy is the solution, or should be a solution to that issue of critical raw material supply. But not only that, it also, of course, helps with well, avoiding waste issues related to PV modules, etc. So I'm really happy that that Malte was willing to join us today to talk about his work on the recyclability and the circularity of PV modules. So yeah, so thank you, Malte, and with that, I would just like to give you the floor.
Thank you for the kind introduction. Let me start sharing. So please stop me if you don't see my slides.
We do see your slides.
Okay. So I extended the scope a little bit. I want to talk about issues with PV growth, and maybe before I get into that, since we have such a diverse audience, I also want to introduce the PV&D group in Delft. So our group mission is to supply what we see here, which is maybe the largest man-made machine on Earth, the electricity grid, with PV systems which provide green electricity for sustainable growth and electrification of society. So this is what it can look like. It can have many forms. It can be added to our cities, integrated in building, or added to the rooftop. And it can also be on our cars, on our roads, charging our bikes, our homes, and it can be above agriculture. It can float on lakes and supply our grid. And in our group, we work on different focus areas. So one of them is developing the next generation of high efficiency tandem solar cells with efficiencies above 30%. Then we try to create smart modules and power electronics to supply our society. And we cover the whole value chain from materials to cells to modules to systems. And this is divided into 5 research areas, 2 which cover the whole value chain. One of them is PV multiscale modeling, and the other one is the circular photovoltaics, which I'm in charge of and we'll talk about today. But the other 5 cover different sizes. So here you see the size scale from micrometer to kilometer, and here you see the power output from microwatt to megawatt. And we start with crystalline silicon solar cells, which are the workhorse of PV today. About 95% of all cells worldwide are crystalline silicon solar cells. And then we work on the next generation perovskite tandems. And we also worked on silicon-based storage. And we combine this into smart modules and power electronics. And our cities in a research line which we call urban energy. But now let's start focusing on my key points today. So first is PV growth. So here you see what happened to PV in the last decade. So we had an average annual growth rate of 25%. And if you think about it, that means that about 80% of PV modules were installed in the last 4 years at any point in time in this scale. And this year we reached about 1 terawatt peak. That is 1,000 megawatts of installed PV. And we started about 70 years ago in the 50s with Bell Labs. So it took us about 70 years to reach the first terawatt. But we need much more than this. And hopefully we will reach the point in the near future where we will install 1 terawatt per year. And over the past decade, we see a price reduction of 91%. And when the decade started, wind energy was the main hope for to combat climate change. But recently, in the latest results, solar energy has been become more promising in terms of CO2 reduction. And so we have to electrify our society and use as much solar and wind as we can. And here I'm gonna show a study on growth rates, and they just start with the Paris climate goal of having net zero emissions in 2050. And here on the dots are the PV capacity in the past few years. And this is where we were last year, about 0.94 terawatt. And now we have reached 1 terawatt peak. And then you see the growth that we need up to about 70. And the blue curve is the installed PV, and the yellow curve is the cumulative. And you see that they are nearly in lockstep. So until 2040, if this optimistic growth rate happens, vastly all PV will be first generation. And only in 2040, we will start replacing it on a large scale. So this is to do that the lifetime of PV modules today is about 25 to 30 years. And pretty soon, in about 10 years, we hopefully have a 1 terawatt annual market. And remember when I told you that this is the first terawatt took us 70 years. And so this is quite a jump, and there are many, many challenges. So one is that we will have millions of tons of cumulative waste. And the other one, if only this growth until 2050 happens, we will use 60% of the silver reserves. So already today, for 200 gigawatts or 0.2 terawatt, we used 10% of the annual silver supply. So in terms of silver, we will really hit a wall pretty soon. So the key lesson is that we need to fulfill the Paris Climate Agreement. We will need PV growth by a factor of 20 to 70. And one thing that can limit this is critical materials. So here is the latest plot on critical materials by the EU, and you see the economic importance and the supply risk. And for crystalline silicon PV, there are really three materials that we need to be worried about. And one is indium, two is the silicon itself, and the last one is silver. It's not considered critical yet by the EU, but for PV, I mentioned already, it's really critical, and it's a challenge that it's not currently on the list to do research in this area, because if there's research on critical material, it mostly covers materials which are red on this list. So let's go through the three materials and I'll tell you where they are used. So the first one is indium. And the funny thing about indium is, if you look at PV today, it's hardly used. But the most efficient solar cells, single junction solar cells that are produced are silicon heterojunction cells. And they use indium as their main TCO layer, which is a layer that needs to be optically transparent and with anti-reflecting properties, and also passivating the surfaces and offer some lateral transport. And so the most efficient solar cells which can be made today are made of this with this material, and they have not yet entered the market, but the pilot lines are out there, and several companies are scaling them up. So one challenge is that optimizing PV and optimizing costs leads us to use a material which is on the critical scale, and that, yeah, which would limit growth. Second is silicon, and we have reduced the use of silicon. So 10 years ago, we had wafer thicknesses of about 300 micron, and now it's about half of that. And we try to shave another 20 to 30 micrometers of that. The difficulty is that at 100 micrometers, it becomes really tough to handle the cells without breaking. So it's really a mechanical issue during production and during the lifetime of PV. But yeah, it's a main driver in cost. So there's lots of incremental research by companies to optimize the silicon use, and also recycling the waste process products from sawing. So there's a lot's done. And to come to the third material. So here we see that about 8 milligrams of silver are used per cell today. But when you think that one cell is about 5 to 10 watt, depending on the size, then it becomes clear what large amount we are using. And we also have to note that we already reduced silver. So on a per cell level, we were using 70% more silver 10 years ago. So we expect this trend to continue by making smaller contacts. But at some point, the cost is not going to be worth it, and we are working on alternatives, which is certainly copper-based. There are different ways of making the copper contacts. One of them is plating, and these are the things that we optimize for in PV. But the most important is that it has to be reliable, so it has to last for 30 years, and it has to be adaptable to mass production. And when I say mass production, factories today, they produce 10,000 cells per hour. So it has to be really quick and on large areas and large quantities. So we are also working on this in Delft, and my colleagues made a copper-plated solar cell, which is bifacial. So it can has the same efficiency from the rear side as for the front side, which is another thing that increases yield and reduces metal use, and it has 22% efficiency. So it can have comparable efficiency levels to silver. And the main thing in the next couple of years is to scale up copper plating. So this is my second key takeaway. We need to reduce and replace critical materials, which for crystalline silicon PV are silver and silicon today. And if silicon heterojunction cells enter the market, also indium will become critical. And now let's go to PV recycling. So here I already gave you these numbers that we will enter a annual market of around 1 terawatt. And this is the associated mass plotted here. So we will have hundreds of millions of tons in our PV system in service, which is the yellow line. And the blue line is the cumulative waste out of service. And here we see that there is a lag of about 20 years between this. So currently we have the issue that there's really on a per country basis not enough PV for dedicated recycling out there. But we are already producing what will be the large amounts of PV. So we have about 10 years to figure out a way how to recycle the old modules, and maybe also how to design new ones which are easier for recycling. And in 2012, PV was added to the e-waste laws in the EU and also several other countries. And they state a collection rate of about 85% and a recycling rate of 80%. And that sounds good as a first impression, but it's actually not quite as impressive once I go into this further. To do this, we have to know what a PV module is made up of. So a typical PV module consists of a frame at the bottom, which is made up of aluminium, and it protects the edge, it makes handling easier, and so on. So then there is the glass front cover, which is about 3 millimeters thick and is the main weight of the PV module. And it's not regular glass for PV. We need a very transparent glass. It's even more transparent than window glass. So we need low iron amounts because iron causes absorption. If you see old glass, it's sometimes a little bit greenish, and then you have lots of iron. So we need about 10 or 20 parts per million of iron ions in our glass to be, that is the current standard for PV. Then we have polymer encapsulant and backsheets, which mechanically buffer the cell layer and allow for some flexibility. But most importantly, they are an adhesive, which keeps everything in place. And the drawback when it comes to recycling, that everything is glued together and it's hard to separate. And then you have the cells in the circuit with most of the valuable material. And you have the external copper cables, which are also quite valuable in terms of material. So now let's look at the mass. On the left hand side, you see the PV module distribution by mass. And what I already said, about 70 to 75% of the PV module's weight is glass. And then you have the polymers, and about 10% is the aluminum frame. And just 3% are the cells themselves. And 1% is the external copper cables. And a PV module, just today, in terms of handling, it's about 2 square meters large, and it weighs between 20 and 27 kilograms. So it's quite heavy. And if we go by value, silver, which is less than 1% of the mass, is actually currently, in terms of material, half of the value in there. And second is silicon, is aluminium, which, yeah, it has about 10% of the weight in the frame. And then third is silicon. It used to be more. So right now silicon prices are quite low. This can change, and then it might be a larger share, but right now it's at about 11%. And copper and the glass. And the polymers are worth hardly anything. So these are the materials that we would like to get back in recycling. However, what happens now, we have a law that states we need about 80% of materials recycled. So we take the glass, we crush it, and we use it as low-level filler material, not even window glass, which would also already be downside. We use it as filler material in roads and maybe glass wool if we have a higher level process. So that's really a pity. And also the other thing, the external aluminum frame, which is 9%. So together we are, and the external copper cable, so we are at about 85%. And we put these in, they are easy to extract. We put them in to our metal recycling, and we're at around 80%, and we fulfill our current laws. And there have some studies been conducted over the years, and already more than 20 years ago we had about 60% recycling rates, and now we're around those 85% by just downcycling the glass and recycling the external metals. And then there are some studies which reach 90 to 96%. And those are studies which really recover the valuable materials. But yeah, we're not, that's just recovery, that's not circular. So that's the current state. And next I will talk about what we would like to be the process. So the first step is already happening today. We remove the external metal frame and the junction or terminal box, and then we get about 10% of the weight and the external metal. Next, we crush the glass and we eliminate the encapsulation polymer, and this can be either burned away or some chemical process, or it can be crushed and then separated. And then there should be a recovery of the silicon of the silver later on, which is the goal, which are the most valuable materials. And we have to differentiate. 95% is the crystalline silicon, and for these we have a different valuable material than for thin film silicon, which has a market share of about 5%. And there we get a different bill of materials which can be recovered. And there is no law or regulation on which materials can go into a PV module. So in theory, anything can be in there. So that's also a challenge when you get a PV module. It's unclear what the, you have some general experiences, but yeah, it depends on the manufacturer and then on the year, what exactly you have in there. And it keeps on changing, so you will need to adapt your processes from year to year with the modules that come in. And now to give like maybe a more outlook, what could design for recycling look like? So there is this mechanical pressure module, or NICE module, which was proposed in 2004. And it basically, in between the cell, we have an under pressure natural gas. And this means that it has to be airtight, and you can, it's essentially a technology similar to double glazing windows, where you have two glass layers with an under pressure, which are sealed at the edge. The only difference is that we need PV cells in between. So this is about in terms of thickness, maybe 0.5 millimeter of edge. And they are glued to the glass, and then you need to extract the current. So the edge seal needs to be airtight, but still have cables going through it. And there are several advantages. So this is designed for recycling because you can just remove the edge seal, let the air in, and then everything is easy to take apart. You have perfect transmission from the gas encapsulation. You have no degradation from the polymers. The most common one is EVA, and it's soldering free. So you have a low temperature process. But the disadvantages are that you have a different refractive index, so you need anti-reflective coatings on the inside and or different anti-reflective coatings on the cells. And you need to maintain the airtight seals for 30 years. And the other disadvantage is that the company who tried to sell them, Apollo and Solar, went out of business recently. So you cannot buy these anymore, and they were a niche startup product anyhow. Wait. So with this, I come to the conclusions. So I showed you that to fulfill the Paris Climate Agreement, we project that we need a growth of PV by a factor of 20 to 70 in the next 30 years. And that in order for that growth to happen, we need to reduce and replace the critical materials, which is mainly silver and silicon and possibly indium in the next few years for crystalline silicon PV. And I showed you that sadly today PV is mostly downcycled in terms of glass and aluminium. And with this, I would like to thank you for your attention and our funding sources. And here you see all my colleagues. So we're a team of about 90% people working on this.
Thank you very much, Malte. I'll give a hand that you can hear, but you can see a lot of virtual hands as well. So thanks for this great presentation. I think it gives a very nice overview of the challenges that are ahead, that lie ahead, but also give some insights in possible solutions to that. So thanks for that. I'm sure there are many questions. I have some myself, but I'd like to give the floor first to someone that wants to raise a hand, or Benjamin.
Yeah, hello. So you mentioned one design for recycling approach. Do you have any other nice examples? Like, this is a really cool approach. I never thought of this, but I'm just curious about more different types.
So there is this Dutch company, Solage, and they have a approach where they eliminate the glass and use polymers only. So they have a different module makeup. So basically, they remove the glass, and then you have a thin polymer sheet, which is transparent at the top. And instead of a back sheet, you have a thicker polymer layer, which then gives the stability that the glass usually gives. So they move the stability part from the front to the back, and then they have all polymers, which they somehow can remove. I don't know the details of the chemical process, but yeah, by having all polymers, somehow they have a recyclable process.
And what was the name of the company you said?
Solage, like
Solage.
solar and large, and then the overlapping 3 letters are basically put together.
Yeah.
And it's a Dutch startup, so they are now in the process of building their first factory, and that is supposed to be 400 megawatt, so less than 1 gigawatt. So it would be less than 1% of the market if this happens in the next couple of years. But yeah, they have an interesting design that can also be recycled. And then there is First Solar. they make thin film modules, and they use cadmium telluride modules, and tellurium is toxic, so they had to think about this for a long time, and they basically have a model where they recycle their own PV modules. No, it's not on here, but they claim recycling rates of I think above 96 to 98%. But this is again a niche product, and only one company which handles everything. So that can be an advantage if the company recycles it itself, then they know what's in it. But that's not the norm.
And one of these
Thanks.
companies you mentioned, First Solar, I think, they were complaining that Chinese panels use a lot of PFAS, which makes it really hard to recycle. Do you have any comments on that?
Use what? I didn't.
Yeah, I don't know. What does PFAS mean? Renee? It's the stuff that all the Dutch are really concerned about.
Yeah, it's a fluorine compound that is often used, for example, in Teflon, like things. So, for example, in in pans and things. And
yeah, and it doesn't degrade. So it's like if it's in the nature, then it never goes anywhere.
Fluorine something.
Yeah. So this is commonly used. Fluorine is used in the backsheet. So you have a polymer layer to isolate the rear side. So yeah, that's an environmental issue. But nowadays you're moving also to different module designs where you have a second glass layer at the rear. So then you can replace that. But about 25% of the market use second glass layers now, so 70% of the market use back sheets, and some of them contain fluorine. That's true.
Yeah.
Why?
It has something to do with making the back sheet durable, but I don't know. I'm not a chemist, so I don't know the details of this. I'm sorry.
Okay, thanks.
Okay. Let's move to Bernard.
Yeah, hi Malte. Really great presentation. I think that's a fantastic overview that you gave here. I have one comment and one question. That the comment is that I think in terms of recycling, it seems to me that the frame and the glass, basically the encapsulation of the solar cells, that's really just a standardization issue, right? If we, in principle, an EU could say, well, this is the standard frame solar cells have to use, this is the standard glass solar cells have to use, and this is where the nuts or this is how to take it apart, and then PV manufacturers can focus on the content of that, and then you can build some robots or whatever machines to take that apart, visually inspect it, whether it can be reused or whether it has to go into a remelting of the glass instead of using it for roads. I mean, that sounds terrible. And on the other hand, I think the hard challenge of recycling is really in that inner layer, right? Because that's where the valuable materials are to a high degree, and there are lots of evolvement in the chemistry over time, etc. That's my comment. Maybe you have something to say on that as well. My question is really, how do you, as a PV expert, see all of these developments of the more efficient but more complex solar cells? Is that something, a direction that is good? Good and bad is maybe a difficult terms, but should we, I don't know, should we go for simple? You were mentioning getting rid of the critical materials, simpler, less critical solar cells with maybe mainly silicon in them, or should we go towards multi-junction, very complex, complicated material solar cells?
Yes, so maybe the first issue, I totally agree. So solar cell sizes are not normed. So if you have a certain size and that's fixed and certain way to take it apart, and maybe there needs to be a bill of materials, then that would help a lot with improving recycling, and also maybe guidelines on that glass should be reused ideally, or that maybe manufacturers have to use a certain percentage of glass again, so they care more about retrieving it intact. Because one issue, when you take apart a plant, even if it's still working on the plant, it sometimes doesn't survive the transport because people taking it apart think this is waste. So there needs to, a lot needs to change. But at the moment, when you talk to recycling people, it's also a problem with the mass that we currently have. So right now, on a per country basis, this is global. We have maybe 10,000 tons, and people say if we build a dedicated plant, it runs for a few weeks and then there's nothing there in the whole country anymore. So the part of the problem will take care of itself by increasing mass. But yeah, there's no money in recycling. It's the main problem. It's still too cheap to use raw new materials. And then
I think that's sorry, go ahead.
I wanted to move to the second part, if that's okay, or do you want to have a
sure. No, absolutely. No, go ahead.
Yeah, so I think we need both. So I think using indium is a trap. We shouldn't do that. There are PERC cells and TOPCon cells, which are maybe 0.3, 0.5% less efficient. So I think there we can just avoid using indium and be fine. But for some applications, we need higher efficiency. So if we want to have PV on cars, there's limited area, and there we probably need tandems. So I think we should develop both, and maybe at some point, like if we can move away from silicon in I don't know 30 years, then that would also be an improvement. So we should keep on researching new materials, but they probably won't help us with the energy crisis in the next 20 years. I think we need to solve the climate change issue based on silicon single junction cells mostly. And there I see PERC and TOPCon as the main workhorses. And why do we still look for more efficient cells? So the PV module is less than half of the cost when I build a PV plant. And so that means if I have a more efficient one, all the other part scales with that. So that's why it makes sense to pay a little bit more for a more efficient PV cell or module, because my financing, my land cost, my construction cost then goes down, because with the same area, I produce more electricity. So that is the argument against or for making PV more efficient and using those materials, that we use less land, we use less concrete, we use less aluminium in the construction, we need less money. So that's really a economical problem, more or less. And right now the economics are skewed towards making the PV more expensive and putting more rare materials in there and reducing the land and construction labor cost.
I think that's a very good point, and I think what you can also see is, of course, that These economics and the business cases for recycling, for becoming circular, for design for recycling, using some materials or not, that's all business case related basically, and somehow there are all kinds of ways in which you can influence the business case, of course, by having certain regulations or obligations or in place that can help you. Standardization can help, making available the tools to separate the modules, having guidelines that make it so that you have to reuse some of the materials or recycled input requirements or things like that. So we somehow this business case, if we want to go in that direction, we somehow have to influence this business case as well, because it won't happen by itself. The market itself will not solve this issue, I think, in a sense. Let's go to Jaco. You had a question?
Yeah, well, even more like a response or an addition to this discussion. So I really like this discussion, and I think Malte has said that, but mentioned that. But he's one of the tenure trackers that have been appointed as part of the TU Delft Climate Action Program. Actually, of his proposal, I was also one of the co-applicants, and I was especially on this that part that he did not refer to, but not really covers, because he's working more on the technical side. That we're actually within this flagship, there also need more policy and innovation extension, and that relates quite well to the kind of work that I've been doing and also been developing. So I just want to mention that I'm looking for a postdoc that can work on the reuse of solar panels, and that's linked to the city of Amsterdam. There's also a sustainability challenge group working on that. Pirine is here from that group, so that's really nice. And that also it raises a lot of interest, and indeed that is because of the more technical aspects development to raise the efficiency and cost reduction, but that's not necessarily the best for turning it into circular business models. And we actually had also, so with colleagues from Malte, we had a proposal on circular thin film PV with Hyatt, also to not only develop the better product, but also to let that co-develop with circular value chain. So there's still a lot of work to be done, also because most of the current solar panels go into the say upscaling waste management system for this part, but that is then going to applications of lower value. Well, there is a lot to gain to design much better for circularity and reuse. That's what I wanted to add to this discussion. So that's most so maybe I should ask Malte, because we didn't really have an opportunity to talk about this, what his views are, how to connect to this kind of research in the kind of work that he is currently developing and doing.
Yes, so I think we need to develop the processes on recycling the current product, while at the same time coming up with alternative ways to fabricate them that are maybe more circular. So I think we have to do both. And for the current product, I think except for the external metal parts and the glass, everything else probably needs to be melted down and then re-enter the material stream. But maybe we can come up with similar approaches to the NICE module, which lend themselves to refurbishment and repowering and repairing. But yeah, I think we need both.
For sure. I fully agree with that. And we also need something like quality standards that we can rank what is on the market on levels of circularity and maybe sustainability.
Yes, but
so there's a lot of additional interdisciplinary work to be done.
Yes, but also we need to remember that in the EU, we currently have hardly any production in terms of PV. We had some about 10 years ago, but that all went away due to this massive price reduction. So if we want to be a player, then we also have to think about getting the industry back to Europe in parts, because otherwise China, which is about 70% of the PV value chain, they will dictate what goes in there. And there is a lot of countries which will buy them because it's the cheapest form of energy. So if we want to set standards, we also need to think about how to manufacture them in Europe again.
Yeah, and that's say why I plead for an additional policy perspective. Also think in terms of scenarios what may happen and what may lead to even industrial policy recommendations. I see that kind of work now appearing for energy and the energy transition, but I don't see it yet for the materials and the circularity of the energy transition. I think it's highly needed.
Yes.
Thanks, Jaco and Malte. Let's move to Perrine.
Hi, nice, thank you. I also have a comment and a question following up. A comment is that there's going to be a really interesting conference taking place in November by Solar Plaza, specifically on circularity, recyclability of solar panels, and the whole energy transition and how we can make it not just not just supposedly green, but actually green, and not just greenwashing a new market for a lot of big players. So yeah, if you're interested, I'm going to put the link in the chat. And I had a question to Malte about the soldering-free design of Apollon Solar, because I don't quite understand why it's solder-free.
Okay, so yeah, thanks for sharing this conference. So maybe first, if you compare solar to coal or gas, it's more environmental friendly by about 2 orders of magnitude in terms of CO2. So I have to disagree a little bit. It's a huge improvement, but we can do better in the future. And in terms of soldering free of the nice module, so soldering has the problem that it needs to use lead, which is toxic, and we would like to avoid it. And it basically keeps the contacts in place. And in the nice module, everything is under pressure and glued together. So we use polymer glues, or I don't know what glues actually, to keep the metal contacts in place. So they are glued onto the glass, and then we have an under pressure. So the contact is created by gluing the strips to the glass and then keeping everything in an under pressure. So we don't need the solder to keep the metal on metal contact.
But then doesn't that defeat the whole purpose of removing the EVA lamination? Because right now what you're saying is, and what Apollon was trying to do, was to design for recycling. But a huge problem with their design is that they still end up using glue, and the most valuable materials, which are the silver and the cells, they end up being glued together in the end anyways. So how does this how is this in any way better than just laminating it all?
Well, because the glue is in specific places, so it's not on the whole area, and you can use different kinds of glues that you can basically attack and target.
Right, yeah. I do want to say that it is possible to solder lead-free. That's a miss.
Yes, that is true, but that's not currently done in PV, at least.
Not yet.
Thank you, Praveen. Stefano.
Yeah, hi. Thanks, Malte, and apologies I jumped into your talk. So if I'm asking something that's been already discussed, apologies for that. One note on what you said, the bringing back the industry to Europe. We have had a number of projects with developers, technology developers of new generations of tandem solar cells. We have been working on perovskites in a couple of projects, and that was exactly what especially the German partners in those projects were saying. They were hating Merkel for killing the PV industry in Germany as well. So we felt that in those projects. But I had a question related to also other kinds of in these kind of projects. We also looked at the importance of the end of life in the environmental performance of such technologies. A lot of the studies that exist out there skip the end of life, so the aspects related to what happens in 20 years from now to those technologies. So we have been focusing on that also, not only on the environmental performance of those technologies with life cycle assessment, but with risk assessment, trying to understand probabilistically what could happen to whatever end of life scenario you create for those solar panels, the existing ones versus the future technology ones. So I was wondering to what extent you also planning to link your work to risk assessment and to potential exposure pathways when handling these PVs at the end of their lives.
So I'm at the beginning of setting up my research line, and I don't think I will focus on risk assessment. I see this research line really as a connector between traditional PV research, which is focused on improving PV by improving efficiency and durability, and industrial ecology. So I want to be able to talk both languages and bring them together, because apart from a few projects, I feel like there is a lot of talk in parallel happening, but not with each other. So that's how I see it. And I want to take that understanding of both worlds to work on technical solutions, mainly to solve the problems.
Yeah, sounds good. It would be good to keep in touch. We are now working with our IBM on a follow-up project. It's called Change, also with colleagues from TU Delft. So working also on the social dimension with agent-based modeling. So understanding how the system will develop in the Netherlands and understanding then probabilistically what matters in the evolution of the solar system, at least in the Netherlands. So it would be nice to keep in touch.
Yeah, I would really like that.
Thanks. I have two brief questions. We have a few minutes left. Maybe they can be quick. So one question is, so you show this graph in which the value of the materials and the mass of the materials are connected to each other, or at least shown in one graph. The material value of different technologies is very different. In batteries, it's really high. Materials are a key component of the total cost of the product. For motors, for example, it's much less so. It's much more the design, etc. How is that for PV cells? How much of the value of the product is actually in the materials?
So it depends on how you look at it. If you look at it on a system level, I mentioned the PV module itself is less than half of the system cost.
Yeah.
So the other half is financing and installation and land.
Yeah, but if you just look at the module.
If you look at the module, it's actually the majority.
Okay, so the majority. But is it then, let's say, because sometimes there's a discussion about whether it's the for example, for metals, you could say, well, it's this specific type of application in the product, or if you just would look at the raw material cost, basically. So how much silver is in it, and what does silver do on the world market? So is it then still more than half?
Yes,
okay.
the raw material, like the challenge is that we need very pure materials for the glass and the silicon, which makes them quite expensive.
Okay. Yeah, thanks. Yeah, that's a good to know. And I had one other question, which I forgot again. Oh yeah. One other question. The perovskites. So there's a lot of fuzz and a lot of buzz about perovskites and what they might do in the future and whether we will need these silicon cells in the future. In any case, or that in, let's say, 10, 15 years from now, all the cells, all the PV cells will be perovskite. What's your view on that?
So there is a lot of research done on perovskite. It's really exploding. But if you go to the market, there is not a single company that sells them market ready at the moment. So there are startups that are working on towards that, but you cannot buy them. So if we wanna, I don't see them happening like within the next 10 years.
Okay.
And then it's probably gonna be, but if we look past the next 10 years, then certainly. That it's a good chance, but the challenge with perovskites is the stability.
Yeah.
So even if they are stable in the lab, what happens outdoor where PV modules have temperatures of, I don't know, 70 degrees, even if everything works well?
Yeah.
What happens under partial shading? So there is a lot of stability issues, and PV is usually a long-term investment. So you need insurers backing your product.
Right.
And
Yeah.
those are the things.
So it still has to prove itself in real life circumstances, basically, even if it's stable in the lab. Yeah. Thanks. Well, with that, I think thanks again, Malte. I think a very insightful and very useful talk in this series. So thanks again for joining our talks. Keep an eye on the agenda. Maybe there's something else that you find interesting, even if it's not PV in the future. Thank you all for joining again, and I hope to see you all with the next series of talks.
René, would you have a few minutes left after this meeting just to catch up on a few things?
Sure.
Good. And thanks for everything. It was a really nice discussion and presentation.